Okay, let's talk about decision trees. And I'm gonna try to convey the concept through a simple graph, a simple plot. In the end, you want to classify. And let's say your classification problem is whether someone, a person, is fit or unfit. Okay, and then you go ahead and collect data on the people in your data set. The decision tree is gonna, for instance, look at the age. This is one of the features in your data. It's gonna look at the age of that person and say if they are less than 30, they are, you go either to the left or right. So if the age is less than 30, yes, you go to the left. If the age is bigger than or equal to 30, you go no. So you ask a question. What is your age? Less than 30, bigger than 30. Left or right? Is that person eating pizza? Yes or no? If they are eating pizza, and then you're going to classify them as unfit. If no, they are probably fit. If they exercise, even if they are over 30, they are fit. Otherwise, no. So that's what the decision tree does. Why is it useful, a decision tree? You want to, let's say you work at a bank and you have a customer. The customer comes into your bank and says, these are my features, give me some loan. This is my age, this is my social security number, this is my history of paying back, this is my credit score, etc. Give me some loan. And then you're gonna run that person through your decision tree and in the end say, yes, we are gonna give you a loan, or no, we are not give you a loan. But the cool thing about decision trees is that they are highly interpretable. Let's say a customer is not approved to be given loan. Their application is denied. They're gonna come and tell you, why did you deny my application? And the bank has to reply. They say, okay, we looked at your age, we looked at your credit score. Actually, they shouldn't look at your age. We looked at your credit score, we looked at this and that's why we rejected you. And that way, they're not gonna be able to sue the bank. So being interpretable is very important. And these decision trees are highly interpretable. Now the question is, how do you train a decision tree? So you have a couple of degrees of freedom to decide. First of all, what should be the first feature that you're going to use? Should we use the pizza feature or the exercise feature first to divide? So you have a bunch of columns. Which column in your data are we going to use first to do the first division? Okay, that's one choice that you can make. The choice of X is the choice of your features. The other choice is this number. Why is number 30 magical? Why didn't you use 29? Why didn't you use 40? For continuous variable, the cutoff point is important. So which features go first, which features go second, third, etc. And these cutoff points are the ones that you're gonna adjust through your training to come up with the best tree that's explaining your data the best. And to make these decisions between which feature goes first, which feature goes second, and what number should I use here, there is a concept called information gain. So how much information do I gain if I put the pizza feature here rather than the exercise feature? How much more information is this going to give me? And if a feature is giving you more information, it is more discriminative, then that's the one that you're going to use here. And that's the way that you're going to train the entire tree. But once the tree is trained, it's highly interpretable and you can use it in practice. And actually, one of the reasons that people use decision trees a lot is because they are interpretable and they are still a powerful method. But what package in R, any questions about the method? And what package in R are we going to use for that? That's library rpart. And we're going to use rpart plot for doing cool plots. Okay, we load that. You have to install these two. Then the way that you use it is very similar to how we were using the other methods. SVM, neural networks, logistic regression, etc. So it's the same command. You feed it your data. Then it's going to train. The training went really fast. One of the parameters that you can control for your tree, you don't want your tree to be too complex. If it's too complex, then it's going to overfit your data. It's going to memorize your data. It's a powerful model. So they usually put a constraint on the depth of this tree. How deep do you want to go? I think for this one, it's around 100. That one you can check. You can sell help on our part, and it's going to tell you how deep your tree is. And now I'm gonna call r part plot on the model, and then it's gonna do the plotting for us. It's beautiful. And this is your entire tree. On the diamonds data, we know that for diamonds data, you have 5 categories: fair, good, very good, premium, ideal. First, it decided that it's gonna you look at the table feature, and if the table feature was bigger than this number, it decided to go to left. Otherwise, it decided to go to right. Based on that, this is all of your data at this location. You're looking at all of your training data, and this ratio at this point, the best one is ideal. This is the biggest number. And where are these numbers are coming from? So ideal is going to correspond to the fifth entry here, and that's the class at this feature. If you cut your tree at this feature, you're going to classify your data as ideal. So with probability 40, it's ideal. With probability 26, it is premium. With probability 22%, it's very good. And with very low probabilities, it's fair and good. But where are these probabilities are coming from? They are coming from counting. You just count the number of data points that are fair. They count the number of data points that are premium. Okay, so this is just counting. Then let's say you decide to go left. Then 45% of the data are here, 55% of the entire data set is here, and out of these 45%, 50% of these 45% or 50% of the observations are premium. That's why you colored this as a premium. You colored this as a blue. Then you look at the depth variable. And if you look at the depth, you either go left or you either go right. This is yes, this is no. Then you look at table again. So you're allowed to look at the same feature twice. And then in the end, you're going to be able to classify your data. Now, when new data comes in, you look at its table. If it's bigger than this number, you go to the left. Then you look at its premium feature. Sorry, you look at its depth feature. If it's bigger than this number, you go to the left. Then you look at the depth feature again. If it's bigger than this number, or if it is less than that number, you go to the right. Then you go to the right, and then you classify that as very good. And that's the probability of it being classified as very good. Okay, not only it gives you the prediction, it also gives you the probabilities. Now you can do your prediction. You look at the confusion matrix, and then you look at your accuracy, and the accuracy is 70%. Any questions so far? So is everything clear? Perfect. So powerful technique, highly interpretable. A lot of people use this in practice, especially in the banking industry. They use that a lot. And that's why many people, after seeing decision trees in these industries, are not that eager to use neural networks because, yes, neural networks are highly accurate, but the problem with them is that it's not interpretable. And for some of these industries, it's very important for your method to be interpretable. You cannot just deny uh, giving somebody loan for random reasons. You need to tell them why they are being denied. Or if somebody is going to graduate school, you cannot just deny them uh, deny their application based on some random feature that you don't know about. Why is it important? Because if you deny somebody because of their age, because of their sex, because of their gender, because of their, I don't know, they have the right to sue you. Okay, so it's very important for your application, for your algorithm to be interpretable. And decision trees are. Random forests aren't. So what is a random forest? It's a bunch of trees. They are not going to be that deep. The idea is that a group of people, it's about democracy, a group of people that make decisions together, they can make their decisions fast individually, and then in the end they can vote. And that's maybe the reason why democracy works. A lot of people vote, and in the end, the best outcome is going to come out. It's the general intelligence of a population. So the idea is to use that. Rather than using a single tree, we are going to use a forest of trees. That's where the name is coming from. And what is it random about a forest? Why do they call it random? One source of randomness could come from your data set. You can take your entire data set and then subsample from it with replacements. And each subsample with replacement is going to have the same size as your entire data set. But then because you subsample it randomly with replacement, this tree is going to see a different data set compared to this one. And this one is going to see a different data set. And because it is with replacement, some data are going to be emphasized more because they are going to appear twice or three times or four times when this tree sees it. Same thing here. Another data set is emphasized more. So that's a source of randomness. So each tree is seeing a different, slightly different data set. And then you do your training, you train multiple of them, and it's exactly what we did up there. It's doing that multiple times. And in the end, they're going to vote. The majority vote is going to win, and it's going to give you your final result. I think I'm going to stop here and then continue the rest of it next session. For those of you who have questions, I'm going to be around. And then the ones who want to leave, we can leave.